Okay, hi Danielle. Hope you're having a good time at your conference. We're going to be talking today about cited derivatives. Hi Danielle.
Hi.
Goodbye. And cited derivatives are one of the topics that requires special care and feeding. We have to be careful in our analysis of derivatives from the left and the right. And the spirit of cited derivatives, where they come from, is that we discover that certain functions are pathological. When Newton first discovers the derivative, Newton-Leibniz, it is believed that functions that were continuous were essentially differentiable, that you could find a rate of change. But quickly it was discovered that certain functions do not actually have a defined derivative at certain points. There's more to this story that I'll share with you in a minute. But I want to give an example of such a function, and that is f of x is equal to the absolute value of x. And when we consider that it's easy to see from the graph that f of x is continuous for all x, then you might think that f of x therefore has a derivative for all x, but it does not. If I ask what is f prime of x, then I find something very interesting. I find, first of all, that I can set up the definition of the derivative. When I set up the definition of the derivative, I'm going to use an alternate form. And that alternate form is going to look like this. We have defined f prime of x as the limit as h goes to 0 of f of x minus f of x plus f of h. Wow, that's horrible. F of x plus h minus f of x all over h. Here we go. And we visualize it like this. If we take a point x and we go out a small distance h, there we go. Keep distracting myself with different thoughts. And we now compute the difference quotient and then compute the limit of that difference quotient. If I relabel the points in this way, if I imagine that I'm looking for a derivative at a point C, and I go out to a second point x, then I would label the points up here as f of x and f of c, like this. And now when I do the replacement, c is equal to x plus h, excuse me, x is equal to x plus h, and c is equal to x, then my limit transforms into the limit as x goes to c of f of x minus f of c over x minus c. And this form of the derivative is saying exactly the same thing as this form, but it is sometimes useful in certain circumstances, and in fact it's going to be useful for our absolute value over here. We call this the alternate definition. Maybe the full spelling. Of the derivative. And in general, it is a very useful alternative to the definition of the derivative that we have here. And we're going to make use of it now to find f prime of x for absolute value of x. We'll do it in the strict form. F prime of C equals the limit as x goes to C of the absolute value of x minus the absolute value of C over x minus C. Now there's a couple of different directions that we could go with this, but I find it to be most useful to rewrite the absolute value of x as the square root of x squared. Does that make sense to everybody? Think about taking an x, squaring it, and then taking the square root. Yeah. And now this sets me up to be able to rationalize. I can multiply top and bottom by the square root of x squared plus the square root of c squared. And when I do, then on the top, I get x squared minus c squared. And on the bottom, I get this. Well, this looks fearsome, except that I recognize that I have a factor of x minus c, right? Now everything comes together. My factors cancel here. I let x go to c, and I get 2c on the top. And on the bottom, I get 2 absolute values of c. So that I end up with f prime of c equals this quantity. But there's a problem. What value of c is going to break the zero quantity? And it's right. So we need to put a qualifier on this, that this is valid only for c's not equal to 0. So that when I look at the derivative, here's f of x equals the absolute value of x in blue. When I look at the derivative, f prime of x equals x over the absolute value of x, then I can see that the derivative is going to be -1 for all x's less than 0, and it's going to be equal to +1 for all x's greater than 0, corresponding to a slope of -1 here and a slope of +1 right here. So all this is fine, but what happens at 0? For what happens at 0, we need to do a careful investigation. So let's do that derivative separately at this point. At c equals 0, f prime of 0 should be the limit as c goes to 0. Nope. As x goes to 0 of the absolute value of x minus the absolute value of 0 over x minus 0. Like so. Oh, I've seen this limit before. What can we say about this limit? There's jump discontinuity. Why is there jump discontinuity? Not because it's piecewise entirely. The limit from the left and the limit from the right are, which often happens with piecewise functions, but that's not the full cause, right? So if we consider now splitting this out into left and right, for x's that are greater than 0, the absolute value of x is simply x. And so I get 1. But for x's that are less than 0, the absolute value of x is actually the opposite of x. And so I get negative. And so we conclude that the limit of this quantity, the difference quotient, fails to exist. And we conclude, therefore, that the function fails to have a derivative at x equals 0. We say that f prime of 0 does not exist. However, it is interesting to us that we had a limit here from the right and a limit here from the left. That told us something. This meant that as my curve comes in from the right, like this, it's going to come in with a slope of +1. And as the curve comes in from the left, it's going to come in with a slope of -1. That's useful and interesting information. So let's actually put a label on this. We're going to label this the derivative from the left at 0. And we're going to label this the derivative from the right at 0. And here's the thing that beginning students will often trip themselves up on. The derivative from the right and the derivative from the left are found by taking a limit. But it's not the limit of f. It's the limit of the difference quotient of f. So let's formalize all this. We're going to define the derivative from the right at c as the limit as x goes to c from the right of f of x minus f of c over x minus c. It is the limit from the right of the difference quotient that gives us a rate of change from one direction away. If I wanted to use the definition of the derivative instead, then I'm going to do the definition of the derivative with h approaching 0 from the right. This is less commonly used, but it's totally legit. Meanwhile, the derivative from the left will be exactly what you think it is. The limit as x goes to c from the left of the difference quotient. Where the limit as h goes to 0 from the left of the difference quotient. And the meaning of these two derivatives is exactly what you think it is also. This is going to be the slope from the right, and this is going to be the slope from the left. You guys remember doing this last year?
Well, we didn't go very deep. We just mentioned that, like, what is correct.
We didn't do a whole lot with it. Elliot? Familiar? Yeah. Honestly, guys, the concept is pretty easy. The devil is in the details. And we'll do an example in just a minute to see what's going on with this. But I want to get the concept across, and let's do a quick, easy theorem also. As soon as you're ready. And that is that the derivative f prime of c will exist if and only if How about, let's say, it equals d? If and only if f prime from the right is equal to d, and f prime from the left is equal to d. In other words, a function can have a derivative if and only if its derivatives from both sides agree. We can call this the two-sided derivative theorem. And we're going to call any function whose derivative exists at C smooth at C. Or we say that f is differentiable at C. Now the proof of this theorem is probably exactly what you imagined. That's the third time I've said that today. All that I'm going to do is to set up the definition here and apply my two-sided theorem. F prime of C is the same as the limit as x goes to C of the difference quotient. And this can equal d if and only if the limit from the right of the difference quotient is equal to d, and the limit from the left of the difference quotient is equal to d, which is just another way of saying that the derivative from the right is equal to d, and the derivative from the left is equal to d. So that we are going to appeal to a big theme in our derivative theorems, and that is that the derivative theorems that we have are going to all be true because of the limit theorems. The reason our two-sided derivative theorem is true is because our two-sided limit theorem is true. Yes, sir?
For the smooth term, would you say f of x is smooth, or f prime of x?
The best way to think about it is we would say that f of x is smooth if it is differentiable at every point.
Every, not like
Yeah.
a certain point.
We would say it's smooth at C if it's differentiable at C. The word smooth is actually kind of context dependent. It really means that f has as many derivatives as you need for whatever. So in the appropriate context, it might mean that f has like up to 5 derivatives in it. So that's our quick and easy theorem. Now let's look at some examples. Ready? The spirit of this first example is that derivatives from the left to the right are not magic. They are simply looking at behavior from left and right separately. So if I happen to know the behavior overall, I'm set. So since I'm looking for f prime minus of 3, I can proceed in one of two ways. I can set up the limit as 3 goes, as x goes to 3 from the right, or I can conquer the whole problem in one fell swoop by finding the derivative, overall derivative at 3, and then appealing to my two-sided theorem. And that's what I'm going to do. I'm going to say that f prime of 3 is the limit as x goes to 3 of x squared minus 3 squared all over x minus 3. And that limit simplifies very nicely with slight bit of factorization effort to give me 6. And since f prime of 3 is 6, using my two-sided theorem, the derivative from the left is certainly 6 also. This example I present first just to give you an element of common sense. But now let's modify our function just a little bit. We're going to take f of x and we're going to break a piece off and replace it with something else. Notice here that I've got a piecewise function, which is always a potential sign of trouble. And if I sketch this either mentally or on paper, what I find is that f is in fact continuous at x equals 3. Take a quick check. Limit from the left is 9. Limit from the right is, oh, hang on, not quite. Try again. There. Limit from the right is 9. That's the function that I intended. And so we think, well, maybe the function has a derivative at x equals 3, or maybe it doesn't. But we're going to have to compute limits, the derivatives from the left and the right separately. And we're going to have to use the limit definition to do it. So I'm going to say that f prime from the left at 3 is the limit as x goes to 3 from the left of f of x, which in this case is x squared, minus f of 3, which is always 3 squared, all over x minus 3. And we've already computed this limit. What value is it? 6. So this guy is 6. But I want you to keep your eye on this, because this is the point where students often get confused. The reason that f of 3 is 3 squared is that when x is 3, the value of f is x squared or 3 squared. And likewise, when I compute f from the right, f prime from the right, I now use the piece of x that applies when x is bigger than 3 for f of x, because this piece is valid for x is bigger than 3, but when it comes to evaluating f of 3, that's still 3 squared. And when this simplifies, I actually get a different value than 6. I get 2x plus 3 minus 9 is going to be 2x minus 6, which is pretty much what you thought it was going to be, because you probably recognized that we had a straight line. Yeah, I guess that's the 4 times 6. Notice here that this made some common sense, because the slope of this line was 2, and so it makes a whole lot of sense that coming in from the right, I should get a 2 for my slope. And the slope of this curve, right at here, I'll put that as slope minus and slope plus. Or 6. How are we doing? Good. Okay, well, let's modify our function yet again. Let's use the one that I almost had for us. If f of x is equal to x squared for x is less than or equal to 3, and 2x plus 7 now for x is greater than 3, then find f prime notice that f prime minus of 3, or f prime from the right, is still equal to 6, because it's the exact same computation we had before. Now when I graph my function, I notice something a little disturbing about it, and that is that my graph is discontinuous. And I wonder what's going to happen to my poor right-hand derivative when I compute it. So let's find out. I'm going to take the limit as x approaches 3 from the right of f of x minus, still with the f of 3, is equal to 3 squared, and all of that over x minus 3. And that's equal to f prime of 3 from the right. Now something tragic happens. And geometrically it had to happen. And that is that when I simplify on the top, I get a limit whose form is actually 4 over 0. Which means that my limit is infinite. And specifically, using sign analysis, I can see that 3 from the right, I'm going to get a positive value here and a positive value here. I get positive infinity for my derivative on the right. And this is the part of analysis that requires our special attention. Because if I were to consider the derivative of just this piece, what is the derivative of just this piece? 2. And if I approach 3 from the right of 2, I get 2. Yeah, right. So watch this. The limit as x goes to 3 from the right of f prime of x is the limit as x goes to 3 from the right of f of 2, which is just 2. But the derivative from the right is not 2. Why not? Because right at x equals 3, my function has to make an infinite rate of change, a vertical jump, in order to go to the next piece. So we have an important distinction. F prime from the right at c is not the same as the limit as x goes to c from the right of f prime of x. That fact crystallizes the delicacy or care that you have to take with the derivatives from the left and the right. So let me say that again. Here is our important fact. F prime from the right at c is different from, in general, is not equal to, could be equal to. So I'll just say is not the same as. The limit as x goes to c of f prime of x. And just recognizing that fact will help keep you from making silly mistakes sometimes. Okay? With that in mind, I have another interesting question that we have just enough time to address. We've had 2 different piecewise functions now that have, in the first case, been continuous, and in the second case, been discontinuous, and neither one of them have had derivatives at 3. So I wonder, is it possible to create a piecewise function in the form f of x equals x squared for x equals 3, and maybe some linear function ax plus b for x is greater than 3? Is it possible to find values of a and b such that f prime of 3 actually exists? probably can. But I think it's fairly clear from the preceding discussion that if this is going to work, then what's going to happen is that my straight line and my parabola are going to have to link up, in other words, be continuous, and also go in the same direction. Derivatives from left to right will have to be the same. So now let's consider, first of all, continuity. I'm going to require that f of 3 be the same as the limit as x goes to 3 of f of x. And specifically, I'm going to require that f of 3 match the behavior as x goes to 3 from the right, because I know already it matches from the left. And so I get 9 equals 3a plus b. Well, that's nice. But it's also an equation with two variables. So continuity is not enough to guarantee differentiability. What about f prime plus of 3 then? What I'm going to require there is that the limit as x goes to 3 from the right of ax plus b minus f of 3, all of that over x minus 3 has to equal the derivative from the left, which we already found is 6. And if this is going to be the case, and I know already that 9 is the same as 3a plus b, see my clever substitution. Then I'm going to have that a times x minus 3 over x minus 3 is equal to 6, or in other words, a equals 6. That drops out. And if a is equal to 6, then I can go ahead and substitute right here and get 9 is equal to 3 times 6 plus b. And so b is equal to -9. And lo and behold, I have found the unique linear function so that the function is continuous with and has the same direction as f of x equals x squared at x equals 3. Yes. Oh. I have ax plus b minus 9, and 9 just happens to equal 3a plus b. So I very cleverly substituted in here and got something. Now it looks like I got lucky because I could pull out that substitution, and I did. So very soon, we're going to find a separate way of doing this. And because f is continuous, the derivative from the left is the same as the limit of the derivative. So back to our observation here, our important fact, f prime of c is not the same as the limit of f prime, but if f is continuous, it will be. So